Section 18.9 Minimization. Introducing the objective function converts the problem of finding the correct key into a minimization problem. The purpose is to minimize the value of the function d of k. Quantum computers work because the quantum state of the system always tends to the lowest energy state. If the quantum computer can be configured so that qubits or groups of qubits represent the values of the variables and the energy of the system corresponds to the value of the objective function, then the lowest energy state will correspond to the minimum value of the objective function. If this configuration can be accomplished, then quantum computers will be able to solve a wide range of real-world problems, including code breaking. To begin, replace the bits in the key with real numbers. Ultimately, these numbers must be either 0 or 1, but it is advantageous to allow the variables to get outside the 0 to 1 range during the search. Start from some initial value, such as setting all the bits to 0.5, or to random values in the 0 to 1 range. Then tweak their values to reduce the value of d of k, trying to get it down to 0. There are many optimization techniques now used with conventional computers, but let's look at just 3. Using these algorithms to find cryptographic keys will require a large amount of known plaintext. At a minimum, the known plaintext should be at least 3 times the size of the key. Section 18.9.1 Hill climbing. Hill climbing, also called steepest descent or the gradient method, is the oldest of the optimization methods. The idea is to start at some point P1 and look at several equidistant points in random directions. Among these points, choose the point P2 with the greatest improvement, in this case with the lowest value of d of k. Then refine the direction by looking at random points near P2. The distance from P2 to any of these points will be considerably smaller than from P1 to P2. Call this point P3. The line from P1 to P3 defines the search direction. Finally, find the point P4 on this line for which d of k is minimum. The search repeats using P4 as the starting point. As the search progresses, the sizes of the steps from Pi to Pi plus 1 are increased each time an improvement is found, and decreased if there is no improvement. This form of search works well when the search space is shaped like a single mountain in n-dimensional space, or a large central mountain surrounded by much smaller foothills. It can fail badly in more complex topography, with many local optima. In this picture, the darker the colour, the better the score. Section 18.9.2 Mille sommets. Mille sommets, or 1,000 peaks, is an idea I used for achieving winning scores in a variety of puzzle contests that I entered in the 1970s. I later started to write up this search method for some computer journals, but I got bogged down in trying to characterize the types of objective functions for which this search method was better than other search methods. The method was rediscovered in the 1990s under the name particle swarm optimization. Picture the search space as a mountain range with many peaks, valleys and ridges. Now imagine a fleet of planes flying over the terrain and dropping hundreds of mountaineers by parachute. In other words, there are many simultaneous starting points. These climbers will look at nearby points to see if those spots are higher or lower. There are 2 variants. 1. You can take only the best one of these points and move the climber there. In this case, if none of the points is better, you reduce the step size and try again. If this fails, say 3 times in a row, then you bring in a new climber who starts at a random location. 2. You keep several of the points that show improvement. You can think of this as the climbing team splitting up into several parties to try different paths. It is best not to take all of the improved solutions, because that quickly concentrates all of the climbers into just a few areas. My original idea was to keep all of the solutions in a heap structure so that the top entry is always the worst solution. You take that worst entry and try to improve it. This proved to be inefficient because you spend a great deal of effort improving poor solutions that you eventually discard. Conversely, always choosing the best solution concentrates all the climbers on a single peak. The best strategy is to choose the next climber at random. In the same vein, when a solution yields several improved solutions, it is not always beneficial to choose the best among these. Sometimes it is better to choose randomly among the several improved solutions. Section 18.9.3 Simulated Annealing. Simulated annealing is a popular optimization technique, mainly because it is so easy to implement. You start from a random point in the search space and look at a nearby point. If that solution is better, then you move to that point with probability B. If that solution is worse, then you move to that point with probability W. The defining feature of simulated annealing is that you change the probabilities while you search. Initially, you set the chance of rejecting a good solution or accepting a bad solution fairly high. Say you reject 40% of better solutions and accept 30% of worse solutions. That is, B equals 0.6 and W equals 0.3. Then, after a time, say after 1,000 steps, you reduce the probability of rejecting a good solution. Perhaps in this second stage, you reject 20% of better solutions and accept 15% of worse solutions. After another interval, say another 2,000 steps, you might start rejecting only 10% of better solutions and accepting 7% of worse solutions. This process is called simulated annealing because it resembles the heat annealing process in metallurgy, where the metal is first heated until glowing and then very slowly cooled. This changes the crystalline structure of the metal to reduce its hardness and increase its ductility and malleability so it can be worked more easily. In simulated annealing, the high initial probabilities of rejecting better solutions and accepting worse solutions are analogous to the initial high temperature state of the metal, and the gradual reduction of these probabilities is analogous to the slow cooling of the metal. Descriptions of simulated annealing commonly refer to the several stages in which the probabilities are stepped as reducing the temperature. Let me pass on a few tips from my own experience with simulated annealing. It doesn't pay to go too slowly. It is a waste of time to reject 40% of improved solutions, then 39%, then 38%, and so forth. At each stage, the acceptance or rejection rate should be somewhere between 1/2 and 2/3 of the preceding rate. For example, 40% in the first stage, then 20%, 10%, 5%, and 3%. Or start at 40%, then 25%, 15%, 10%, 6%, 4%, and finally 2.5%. 5 stages are usually enough. It is a waste of time to start with a 50% acceptance rate. Start between 60% and 75%. It does not pay to go to 0%. You will get greater improvement if the last stage accepts 2% to 3% of worst solutions. Quit when nothing is happening. You may have planned 1,000 trials in each stage, but if you have made 100 tries with no changes, stop. Make the percentages depend on the size of the improvement. For example, in the first stage you might accept 60% of the changes that improve the score by 1%, 75% of the changes that improve the score by 2%, and 90% of the changes that improve the score by 3% or more. Experiment. Every optimization problem is different. Try varying the number of stages, the number of trials per stage, the rates of changing the probabilities, the step size, and the relationship between the degree of improvement and the percentage of acceptance. The hill climbing, mille sommet, and simulated annealing techniques may be freely combined to produce a variety of hybrid methods. Section 18.10 Quantum Simulated Annealing. There are several proposed methods for using quantum computers to do simulated annealing. These methods use quantum phenomena such as superposition to perform many searches in parallel. However, every trial requires evaluating the objective function at the chosen point. Quantum computers are not made for evaluating expressions. There are, as yet, no methods for evaluating these functions in parallel by quantum means. The quantum computer can use a conventional computer to evaluate the expressions, but this loses the parallelism. So far, quantum searches have not shown any speed improvement over conventional computer searches. Section 18.11 Quantum Factoring. The strength of the RSA public key crypto system rests on the difficulty of factoring large integers. Given two large integers a and b, it is easy to multiply them to get the product ab, but it is very hard to reverse that process and determine the factors of a large integer. Factoring a large number has the same degree of difficulty as computing a discrete logarithm, section 16.3, and uses many of the same techniques. This security may potentially be breached by Shor's algorithm for factoring large numbers. This was the first quantum algorithm ever developed, invented by Peter Shor of MIT in 1994. If the algorithm can be implemented successfully for large integers, either RSA must be abandoned or the modulus must be made larger, perhaps millions of bits. So far, using Shor's algorithm, the number 15 was factored into 3 times 5 in 2001, and the number 21 was factored into 3 times 7 in 2012. At this rate, we may expect the number 35 to be factored into 5 times 7 sometime around 2023. Humour aside, it may be decades before Shor's algorithm becomes a real threat to the security of RSA.